Hey everybody. In this example, I'm going to try to focus more on the how and less on the why than in previous examples to see if I can make it a little bit shorter. So we're given this transformation t that maps from P2 to R3 such that T of P is equal to P0, P of 1, P of 2. Now we're not told that it's linear, but we're asked here to find the matrix for T relative to the standard bases for P2 and R3, so we can assume that it's linear. If it's not linear, if T here is not linear, then we can't do this. So we'll assume that T is linear. If we really wanted to, we could check linearity, but I'm not going to do that. Okay, so the first thing we want to do is write down what these bases are. So I'll call B the standard basis for P2, the same basis we've looked at quite a bit recently. I called it D in previous examples, but you can call it whatever you want. And for convenience of reference, let's go ahead and label these vectors B1, B2, B3. And then it's conventional to use capital E here for the standard basis for Rn. It's not necessary, but it's a convention, so we'll go ahead and do that. And in R3, the standard basis is the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. All right, so now we can write down this matrix for T relative to the standard bases for P2 and R3. That's a big, long description, but the definition is in the lecture notes and in whatever book you're looking at. So we'll use the letter M, which is what I used in the notes, and I think that's what's used in lay. So it's a matrix, right? It's the standard, or it's the matrix for T relative to the standard basis here. So then the columns of the matrix, well, the first column is T of B1, and then we take the coordinate vector of that relative to E. So notice I have T of the first basis vector in B, and I take the coordinate vector of that relative to the second basis, E here. Okay, so the second column is just T of B2, and we take the coordinate vector of that relative to E, and the last column, T of B3, relative to E. So it's a little bit complicated, the notation here. Notice these brackets in here indicate the coordinate vector of what's inside. These brackets out here for the matrix are indicating the matrix. So same notation with two different meanings here. Brackets inside here refer to coordinate vectors, and the outer brackets are the matrix. So we're asked to find this. Well, that boils down then to finding what's inside here. Find this one, and then this one, and then this one. So we'll work from the inside out. We'll figure out T of B1 first. So remember, here's B1. It's just 1. Now I'm going to think of B1 as a polynomial here because it's in P2, so it is a polynomial. So I'll call it P of T, say. And it's so easy, it's hard. It's a constant polynomial. So no matter what T is, P of T is 1. So if I evaluate P of 0, well, I just get 1 because P of anything is 1. P does not depend on T. So P of 0 is 1, P of 1 is 1, P of 2 is 1. So I'm evaluating all of these polynomials here that are in the function rule, if you will, for T. So then I can say T of B1 is going to be P of 0, P of 1, P of 2, and I just get 1, 1, 1. So that's the inside of the first column here. I still have to get the coordinate vector of this relative to the standard basis E up here. But we'll do all the insides first, and then we'll get the coordinate vectors. All right, so let's do B2 now. Well, if I call that P of t, that's just t. So back up here, B2 is t, B3 is going to be t squared. So P of 0, I'll plug in a 0 for t here. So P of 0 is just 0. P of 1 is 1. P of 2 is 2. So T of B2 is 0, 1, 2. And if B3, if we write it as a polynomial, P of t is equal to t squared. P of 0 is 0 squared. P of 1 is 1 squared. P of 2 is 2 squared. So T of B3 is 0, 1, 4. So we're halfway there. We actually did the hard part. So I've got the insides of these three. Now I need to get the coordinate vectors. Well, here's a handy fact. This is in the lecture notes as well. If x is a vector in Rn, and E is the standard basis for Rn, then the coordinate vector of x relative to E is just x itself. So that's very handy. And you can look at the derivation or the proof of that in the notes. It's really straightforward. So that just means, for example, the coordinate vector of T of B1 relative to E is just T of B1. And same for the other two. So if we go back up here, we can simplify this. Because this only is true for the standard basis, but because I'm using the standard basis here, it doesn't matter what I call it. I could use any letter I want here, but these are the vectors in the standard basis. If I use these vectors, then the coordinate vectors are always just going to be whatever's inside here. So M simplifies to just T of B1, T of B2, T of B3. So this example is a little simpler because of that. If I didn't have the standard basis here, or here for that matter, this example would be more difficult. Okay, so finally then, we can just take these vectors that we found and put them into the columns of M. And that is the matrix for T relative to the standard bases for P2 and R3. Okay, now let's do part B. Find T of this polynomial in P2 minus 5 plus 7T minus 3T squared using this matrix that we just found. So from part A, I just recopied the matrix that we found, the matrix for T relative to the standard bases. And I put down T here for reference. And this is the defining equation for M in terms of what we're doing here. So what we do, among other things, with this matrix M that we found is we can get the coordinate vector for T of P relative to the standard basis for E from the coordinate vector for P relative to the standard basis for P2 just by multiplying by this matrix. So this is the idea that we're going to do this essentially inside the computer. All of this is, can imagine happening inside a computer. This is a vector in R3, this is a vector in R3, and this is a 3 by 3 matrix. So we're just doing matrix multiplication, and we're essentially implementing this linear transformation using matrix multiplication. All right, this is the equation that we're going to use, and this is how we're going to find t of this vector. Notice it tells us to use this matrix. If we didn't want to use the matrix, we could just go back here and plug in 0, 1, and 2 into the polynomial and figure out what t of p is. And that would, honestly, that would probably be easier here. But for practice, we want to do it this way. Okay, so I just need to figure out what these things are. I've already got the matrix M. I need to figure out the coordinate vector of p relative to b. And, well, we already know the coordinate vector of t of p relative to e. That's just going to be t of p itself. So that saves us a step, because what we're asked to find is t of, well, if we call this p, t of p, and we'd have the coordinate vector here, and then we'd have to reconstruct t of p from the coordinate vector. But since this is the standard basis in R3, as we just saw, we could just say this is just t of p. In other words, the coordinate vector of t of p is just the same as t of p. And the right side stays the same. So we just have to do a little matrix multiplication. So we'll have our matrix. And then let's just write down this coordinate vector, because we're using the standard basis here. I didn't rewrite it on this page. We can jump back real quick and see. Here's the standard basis for P2 that I've called B, and we can just observe coordinate vectors. So if I just look at this polynomial, in fact, let's be really explicit. Let's write over here P of t is minus 5 plus 7t minus 3t squared. So my coordinate vector is going to be minus 5, positive 7, minus 3, relative to the standard basis for P2. So I just write that down. And then you can do this matrix multiplication either by hand or on a calculator, whatever. I'll skip that multiplication step. You'll get minus 5, minus 1, minus 3. So we can just say t of p is minus 5, minus 1, minus 3. And it's just a coincidence that these two values are the same as these two values. It's just because of how the arithmetic works out here. So here's our final answer, and we're done.